Climate change is expected to worsen the frequency, intensity, and impacts of extreme weather events, increasing risk and extent of wildfires, widespread droughts, as well as species extinction. As Canadian author Margaret Atwood once said, "It's not climate change, it's everything change." And how does agricultural land respond to climate change? Corn production in the US is dominated by the Great Plains of central United States, the Corn Belt. The Corn Belt, roughly including 12 states, is one of the most fertile regions, producing more than 10 billion bushels of corn each year. Corn yield trends are positive across the Corn Belt. As darker yellow indicates of more production of corn, we could obviously observe that the centroid of the corn production is moving northwest over the last 50 years. In the highlighted area, mostly in the north part, the yield has increased by over 100%. The shifting of yield centroid is mainly because of the changing climate. As climate warms, plant harvest zone, which tracks average low temperature in winter, are moving north in the US at 13 miles per decade. As the most important crops in Corn Belt, corns and soybeans are planted in plant harvest zone 5 and 6. However, since the plant harvest zone is shifting north, while the more suitable conditions for commodity crops may shift northward to states like Minnesota and Dakotas. The climate model shows a similar prediction. It predicts a rise in average temperature, which will affect crop growth. According to the Harley-3 model, area-weighted average yields are predicted to decrease by 30 to 46% by the end of this century under the slowest warming scenario, and by 63 to 82% under the most rapid warming scenario. Both the shifting of plant harvest zone and the climate prediction model indicate that climate change will probably push corn growth regions north. It is expected to be new corn agriculture in northern states, and the southern part of the Corn Belt is vulnerable due to higher temperature. To maintain the agricultural production in southern Corn Belt, farmers may change the crop type to adapt to climate change. Cotton, for example, is currently dominant in Cotton Belt in the plant harvest zone 7 and 8. As the weather gets warmer, it is likely that the Corn Belt would grow cotton as an adaptive crop in the future. However, by comparing the corn distribution of 2010 and 2021, there is no obvious change indicating the Corn Belt moving north spatially, which is contradictory to the prediction and climate model. The land use of the Corn Belt remains stable. There's even an expansion of agricultural land due to higher corn price in recent years. A study of the migration pattern in the agricultural regions, which reported to be under climate pressure, also shows that there's no significant trend of farmers moving north. As the yellow and green color representing people moving north and south, it seems that climate change hasn't shown an effect on people's moving pattern. As models are predicting the Corn Belt is moving north, despite being aware of this prediction, why aren't farmers moving north as well? As we can see, vast acreage of corns and soybeans are watered by center pivot irrigation in western Corn Belt states, changing a near-desert region into the largest agricultural region in the US. Irrigation and evaporation creates microclimate to reduce the temperature and heat effect. The spatial distribution of changes in irrigated acreage reports a decrease in western United States, and as shown in blue, an increase of irrigation is concentrated Midwest, especially in Corn Belt. Where surface water supplies are insufficient, groundwater is often used for irrigation. Agriculture uses about 53% of groundwater pumped for human use in the US. Taking advantage of this incredible amount of water resources provided by Oglala Aquifer, there has been significant crop production for decades in the 12-state Corn Belt region. Its water supports $35 billion in crop production each year. While these regions are now under more and more severe water stress, as the Oglala Aquifer will be depleted and ultimately exhausted. Once depleted, the aquifer will take over 6,000 years to replenish naturally through rainfall. More than 90% of the water pumped is used to irrigate crops. Among them, Nebraska is the biggest consumer, taking 46% of the annual pumping water from the Oglala Aquifer. The number of irrigation wells in Nebraska has exploded from 100,000 to 250,000 registered irrigation wells since the 21st century, and additional of 16,000 registered water wells. The fourth color satellite images, concentrated in the dense wells area, shows the spread of central pivot irrigation in Nebraska. The bright red colors shows healthy vegetation with irrigation in this fourth color composition. In order to get more information of the aquifers, USGS started the RASA program to gather the monitoring data from national and regional organizations as shown in red circles. The green circle indicates the data users, showing that the monitoring data is not only provided for local water management, but also for agricultural organizations and other international organizations. Cooperating with more local organizations, USGS formed the National Groundwater Level Monitoring Network and characterized a system of aquifers and flow system boundaries. The most common aquifer test is by in-situ test through pumping wells and monitoring wells. The test is conducted by pumping water from one well at a steady rate for at least 1 day, while carefully measuring the water level in the monitoring wells. Calculating the triangular relationship of pumping, image, and monitoring wells, the boundary of the aquifer can be mapped through connecting the midpoints of pumping wells and image wells. To map all the aquifers in the United States, more monitoring wells were built continuously along the boundary of the aquifers. After characterizing the boundary of the aquifers, more monitoring wells inside the aquifer were built to support the further research in aquifers. Through integrating the monitoring data in the local organization and further investigation in aquifer, USGS published the Groundwater Atlas of the United States. The calculations of boundary are based on a conceptual model called Theis equation. However, the equation is based on a large number of simplifying assumptions. Although none of the conditions could be fulfilled in the real world, the Theis equation is still considered the fundamental model for aquifer testing. Groundwater is part of the water circulation. It is recharged from precipitation and canal seepage, pumped out for irrigation, and emerges back to the land surface, into rivers to keep the water cycle going. This process is also used for prediction of future groundwater budgets. To fully investigate and predict the depletion of aquifer, NASA launched the GRACE satellites, and more food companies benefit from its open groundwater data. The researchers are both using direct monitoring data from NASA and USGS, and climate data from National Weather Service to build and train the prediction model comprehensively. As the Oglala Aquifer is depleting, researchers from different organizations have been working on the future prediction. Except for monitoring data, the prediction will also involve the climate data, like temperature, evaporation, remote sensing data, set to estimate the irrigation requirements. Two research groups led by Kansas State University and USGS investigated on this issue separately using different models. Through inputting different data sets, they got two completely different output scenarios. While Kansas State University predicted Oglala Aquifer will deplete in 2110, USGS believed that the depletion was in far future. Although we rely heavily on groundwater resources, it seems there is no agreement on when the aquifer will be depleted. The story happening in western Corn Belt states like Nebraska could be the coming future for the whole Corn Belt. Researchers find states in Corn Belts and Great Lakes where corn growth is primarily fed by rainfall would be subject to more intense but less frequent precipitation. Maintaining crops will require 5 to 25% increase in irrigation, which would in turn require more extensive and expensive water catchment infrastructure. However, as the temperature keeps rising in the coming future, it is likely that more than half of the Corn Belt states would have to use irrigation to feed crops, leading to more depletion of aquifer in the Corn Belt besides Oglala Aquifer. Irrigation may be useful in the short term. Researchers find that crop yields will decline even if irrigation continues to be applied as needed. As we could see that irrigation is unsustainable and costly, it's more like an attempt to fight with the harness zone, changing the microclimate and trying to keep the zone 6 as it is through irrigation. Why do people still keep investing on irrigation? Government payments could be direct support. Massive government payments to farmers hide behind huge water consumption. Federal subsidies increased by a remarkable of 65% in 2020, totaling $37.2 billion. Corn prices were too low to cover the cost of growing in that year, with federal subsidies making up the difference. The subsidies put farmers on a treadmill, working harder to produce more while draining the resource that supports their livelihood. Government payments create a vicious circle of overproduction that intensifies water use. Subsidies encourage farmers to expand and buy expensive equipment to irrigate larger areas. Subsidizing corn production is supporting the U.S. economy. 16 separate sectors, from fast food companies to fertilizer manufacturers to grocery retailers, depend on U.S. corn as a key ingredient of their products or as a market for their inputs and services. In 2013, the top 45 companies in the corn value chain earned $1.7 trillion in revenue, more than the value of Australia's annual GDP. However, we might also find that even these hidden upstream companies are also looking for longer-term strategy. Companies like Cargill, ADM, and Bunge, which are the magnets of the corn manufacturing industry, is buying land all over the world. A new sensing approach in monitoring groundwater storage change can play a role in companies' decisions in purchasing land worldwide. In March 2002, NASA and the German Aerospace Center took the Gravity Recovery and Climate Experiment mission, which they can be also called GRACE. A twin satellite was launched to measure gravity anomalies. Launched into near polar orbit, the satellites are 220 kilometers apart, at an altitude of approximately 485 kilometers. using the precise measurement of the distance between the two satellites, recorded by an onboard microwave tracking system. Scientists can produce a model of the Earth's gravity field every 30 days. By examining a grace-derived gravity model from two time periods, the change in mass can be calculated for a particular region by the observed change in gravity field, while the temporal variations in the gravity field are caused mainly by changes in terrestrial water storage. Terrestrial water storage is the sum of soil moisture, snow, surface water, and groundwater, with models like NLDAS monitoring other land hydrology factors. GRACE can clearly represent the water stress of groundwater depletion. Crop irrigation is closely tied to groundwater depletion, which helps in decision-making of companies' future plans. ADM, for example, is related to collection, processing, and manufacturing of corns. With headquarters in Chicago, ADM now has processing and procurement branches all over the world. According to the data from the Land Matrix, ADM is purchasing land in Africa and Asia. 14 international land trades are completed with the total deal size of over 4 million hectares. With the trend that big companies in the US are purchasing land worldwide, we have reasons to believe that North might not be the only destination for Corn Belt. It's more likely that the US Corn Belt will be international in 50 years.